Hey, my entire physical science class. I didn't see you there. Oh, that's right, because I'm just staring into my iPad and I can't actually see you, but I wish I could. Guys, again, miss ya. Um, hey, I felt the need to put out a video that just covers the whole chapter. It might be a little bit long, but please stick it out. All right, watch the video, pause it, take notes, do what you can. I just want to encourage you guys. You're working hard. Please keep working hard. Everything you're putting forth, it means a lot. It goes a long way in this whole process of me trying to make sure I'm presenting stuff still to you, reading the book, answering the questions. I'm going to go through the whole chapter, all right? So stay with me, keep up. Thank you guys. Some of you guys are sending out the prayer requests to me. Thank you for doing that. It helps encourage me too. It opens up your life to me, and I just want to keep encouraging you to do that. Some prayer requests from me to you. Just keeping my family in your prayers. Listen, this is weird for us too. It's different, but we're doing pretty good. All right. I got to be honest. If you asked Aiden right now, do you like it? He kind of likes being at home, but he still misses his friends, just like you guys too. All right. So I love you guys. I miss you guys a lot. All right. This class right here, we have some real good back and forth banter, and I miss that, all right? Listen, if I'm looking right over there, Kenzie, I definitely miss some banter with you. TJ, my funny guy over there, Xavier over there, the snakes miss you, buddy. Eli in the back, listen, I miss you. You're kind of like that big athletic teddy bear, all right? You got such a kind heart. Schwen, I miss you coming up consistently, asking to try to get one more point on whatever the assignment may be. And let's see, who else do we got? We got Brendan, Yasmin, miss you guys right there in the front row. You got your own funny stuff, banter back and forth, and then towards me. Listen, I miss you guys. I care about you guys. Let's just jump right into it. That's a lot of time between me and you. Okay, let's do this. Okay. We got section 1. We're talking about pressure. You guys already wrote down those key terms. Good. You got to get the equation for pressure. It's force divided by area. Let's talk a little bit about how pressure, force, and area all relate. Okay? So if we're talking about pressure equaling force over area, something we got, think area also as in surface area. All right? There's a question or something in the book that talks about, let's say someone has like a snowshoe, all right? So we're talking a big shoe, big surface area, or you have someone that's wearing like small shoes, like even like high heels or something. That's a really small surface area. So that surface area, if this number on the bottom is small, and then the force on top is just the normal force pushing down, so let's just call it pretty big, all right, then the pressure is going to be big, all right? You're going to sink through that snow if that's what you're walking in. But if you have a big surface area, all right, we're just going to say even bigger than the force, then the pressure is dispersed or displaced or spread out, meaning that you're not going to sink directly into that snow, okay? So that covers that right there. The next thing that you guys got to know, all related to pressure, is that the SI, remember SI is the International System of Units. It was created by the French. They flipped the letters on us. Thanks, guys. The SI unit of pressure, it's the Pascal. All right, the Pascal. But you guys, I'm sure already got that. I'm moving on. A fluid, all right? A fluid could be considered a liquid or a gas. So I don't want you to think that a fluid just has to be like a drinkable liquid, like water. Literally around me right now, there is fluid in the air because air is a fluid. All right? That's something else you guys got to know. And something that I circled, I put it because it's important in my textbook on page 418, the second to last paragraph that says, in a fluid, all of the forces exerted, that's the paragraph I'm talking about. All of those individual little particles in a fluid, in other words, a liquid or air, all of those individual particles, all of those put together make up the pressure exerted by the fluid. So I'm going to simplify that. Imagine that you are in a swimming pool and you're right at the surface and you just barely go underneath the water. You still have a decent amount of water particles up above you, right? But you don't really feel too much pressure. But now let's say you go way down. You're at the bottom of an Olympic swimming pool. There's a lot of water above you. Can you imagine how many more particles of water are above you? Multiply all those particles together. That is how much more pressure is now being pushed down on you. So think of that in relation to deep under the ocean. You go into one of those crazy deep Mariana Trench. That right there, that's so much water. All those particles multiplied together, pushing down on you. That's why when you go deep underwater, the pressure goes up. Again, deep underwater, all those particles multiplied, and now on you, the pressure goes up. Okay? All right. Now, when we're talking about balancing pressure, I'm on page 419, atmospheric pressure. It's pretty amazing. You have atmospheric pressure on your hand, going down, going up. You see the picture. It's figure 3 on page 419. Here's something that I wanted to pull out of the text. Maybe you didn't write this down. All right. If you could imagine that there is about 101,300 pascals of pressure being pushed down on you right now, but yet how am I not being crushed? How are you not being crushed just sitting in your room, I'm sure, right now? How is that possible? Because all of this is being spread around you. It's not just all coming down on, it's on, and it's going up, and it's going from the sides. It's equally dispersed. So the weight, just if you talk about your hand, I'm pulling this right out of the text, the weight that your hand is able to support is 1,000 newtons. That's a huge amount. But yet, why isn't your hand just crushed doing nothing? Because it's equally dispersed. All right? So your hand can support all of that because the weight of the atmosphere does not just press down, it presses up and the sides. So it's equaling itself out. It's like anything you're pushing down, it's equally pushing up. You don't feel that pressure. That's why the atmospheric pressure isn't being felt on you. Okay? They use this picture of a can on 419. I think that's kind of helpful. If you just have a can and you open it up to the air and then you close it, the can's not going to get crushed. But if you take the air out of that can, now you no longer have the air inside the can pushing out. All you have is the air in the atmosphere pushing in, so the can's going to get crushed. It doesn't have that equal opposite pressure pushing out. It only has that big pressure of the atmosphere pushing in, so it's going to get crushed. All right. We already talked about water pressure. The deeper you go, you have all of those particles around you. But what about when you go high up? Yes, you have air particles, but here's the difference with air. Air is a lot more spread out. So those particles are not being pushed on you quite the same like the liquid water particles would be if you are deep under the ocean. So you go up, atmospheric pressure, elevation, atmospheric pressure is dropping. Okay, as you go up, the pressure on you is decreasing. Now here's why your ears pop. Because let's say you're traveling into the mountains, you're going to go camping, all right? You're going up, your elevation, you get up to like 15,000 feet of elevation. That's really high. Your ears are going to really want to pop. Why is that? That's because the atmospheric pressure pushing in on you is actually less than the pressure in your own head wanting to push out. So you need to pop your ears and relieve that pressure right behind your eardrum. You feel it even when you're taking off in an airplane. Same thing. Pop. There goes the pressure, relieves the pressure, and you're going to start to get a little bit more of an equilibrium. Pressure in the head, pressure out of the head, right there. We want them to be that nice equilibrium. Okay, let's keep moving. Got to know the definition of barometer. Sure you got that. Let's go to section 2. We're talking about density. All right, now one important thing, the density of water, it's 1. All right, it's 1, and that is what we base so much off of. Is if we know something floats on water, well then what is its density? It's less than 1. Like wood floats on water, less than 1. If it sinks, it's bigger than 1. And if it's right there really close to it, like if you drop something and it just stays right in the middle of a cup of water, it's probably really close to a 1, equaling water. Okay? All right. So that's an easy way to compare something, is based upon its density. They give you a nice little density chart on page 425. I would recommend writing down some of those examples with their densities and how they relate to water being a 1. All right, let's turn the page. There's this thing called buoyant force. All right, I wrote this little basic chart. You have weight, and in parentheses, I'm going to put gravity, because gravity affects weight, right? So if we have a lot of weight, then gravity's pulling us down a lot more. So this pushes down, okay? And then we have the buoyant force, all right? And this always pushes opposite of weight, opposite of gravity. If you have a greater weight and you are literally sinking in the water, then your weight is bigger than the buoyant force acting against you. Look at the bottom of page 427. They give you a basic picture of 3 examples in the ocean. A jellyfish, well, it is actually very small in weight, and the buoyant force pushes more on it than the gravity pulls against it. So where is it? It's at the top, because the buoyant force is stronger. But then you got that turtle. The turtle can stay right in the middle because, amazingly enough, its weight and its buoyant force are equal. So it can stay right there in the middle of the water, not at the surface, not at the bottom of the ocean floor, and it's perfect. Weirdly enough, the lobster is heavier, so it has a greater weight, gravity pulling greater on it than the buoyant force acting against it, and so it's down there at the bottom. All right? Now, one other thing you could think of is, what about the surface area? Did that play a part in the fact that the turtle has a greater surface area, has a greater volume, meaning internal space that can be filled, and that lobster has a lot of compressed, smaller inner volume, and so the weight that it has over a smaller surface area actually helps to pull it down, because the buoyant force has less to push against than it does with the turtle. There you go, something more to think about. All right, turn the page. Oh, Archimedes Principle. Okay, here we go. We got some weight distribution. We got some, a ship. We got some information about how a ship even works here, okay? Archimedes Principle. Basically, what we are going to do here is, if you have a large body of water, you're talking about the ocean, but let's talk about a swimming pool. Let's think about that. If you have a swimming pool and you're about ready to put a lot in that swimming pool, but the swimming pool's right at the surface, okay? If that swimming pool's right at the surface and you put a lot in that swimming pool, then you are going to have a lot of water slosh out of that swimming pool, okay? Now, here's where Archimedes' principle comes into play. What you put in the water and what is displaced, fancy word for like the water that sloshes out of the swimming pool, those are equal. So let's imagine, look at the top of page 428. You got that nice little picture of a film canister that's empty. You see how part of it's floating and part of it's underneath the surface? The part that's underneath the surface, if you were just to fill up that little part with water, it would equal the amount of water that left the beaker it was put in, that was displaced. All right? Here's the basic picture behind that. All right? Here's our beaker. Here's our water. Here's our film canister. This amount of the canister that's underneath the surface will equal the amount of water that got pushed out when we put that film canister in. Now, if we had another example, and we have water right there, and that whole film canister is underneath all of this right here. If we were to fill that film canister, it would be equal to the amount of water that got pushed out when you put the film canister in. That is the basic idea of Archimedes' principle. Now, how does this relate to a ship? A ship has a big surface area, right? The bigger the surface area, the more water that gets displaced. But also, the greater the buoyant force that acts against it. So this is why, let's say you have a huge ship in the water and it's floating, but you have a big, like a condensed amount of steel that amazingly enough equals the weight of that ship. That steel's sinking. There's no saving that steel. It's now at the bottom of the ocean floor and water's displaced. But the ship weighs the same amount as that steel. What's the difference between the two? It's the surface area that the ship has. It's a great big surface area that allows a lot more buoyant force to push against it. So yes, it's heavy and it's pushing a lot of water down and displacing it out, but the buoyant force acting against it is just as great. So it keeps that ship up. But that condensed amount of steel that weighed so much, that has a really small surface area, it's not going to make it. It's down at the bottom of that trench. All right. Turn the page with me. Let's go into section 3, Pascal's Principle. We're talking about force. We're talking about hydraulic systems. And basically what we have here is if you have, let's get some clean space. All right. If you have a small surface area, all right, and you have a force being pushed down on that smaller surface area, and then it's going through this really small tube, you could imagine that you are actually compressing that force. You are putting it over like a really small tube right here, which is now allowing that force to be like built up pressure. And if we allow that to go onto a bigger surface area, it is now going to be multiplied. How much bigger is that surface area here than that tinier surface area here? It's a lot. Now, what this principle talks about is if you have, I wrote down a little note here, if you have a small amount of pressure, think about you just applying the brakes on a car. That's a good example the book uses. You don't have to push very hard on those brakes, but you are applying a lot of pressure on a small space. So think about a hose, another example. Water's going out of the hose, but then you close a little bit of it, and what happens? It starts shooting out because you decreased how much water could go out, but the pressure coming to you is still the same. Same concept. When you apply that pressure on the brakes, you apply the pressure, now you're increasing the pressure that goes into that small brake line, but then it's dispersed over a much bigger surface of a piston, and that big piston applies a lot of pressure because the bigger the surface area of that piston, the bigger the pressure and the bigger the force it's going to exert on the brake pads. So you got to imagine your tiny little foot applying a little bit of pressure on the brake slows down this big hunk of steel traveling down the road. Now still, you may need to apply more pressure if you got a big hunk of steel like a big semi truck because you're going to need more time to slow it down, but nevertheless it will stop it. All 4 brake pads are being applied at the same time because that hydraulic system that had a small piston a little bit of force going through a small tube, it's built up pressure, it's now exerted over a bigger piston, and another, and another, and another, and that multiplies the force onto the brake pads, all 4 brake pads, okay? So that's the basic principle of how this hydraulic system is working. Last section, section 4, wake up, stay with me, stay with me. I know we're 20 minutes in, please stay with me. Here we go, we're almost done. We're doing a whole chapter here. Basic idea of Bernoullis Principle. All right, we're going to talk about how Bernoullis Principle affects an airplane, how it affects a chimney, those atomizers, if you will, if you're like using perfume, those are like kind of old school. All right, how it affects a frisbee. It's all of this under the one principle of Bernoullis Principle here. So what we're going to say is if you have the perfect shape, you'll notice the shape of an airplane wing, the shape of a frisbee, those are very similar. They are promoting speed on the top, all right? Promoting speed on the top. We have this nice curved shape, and it's much flatter on the bottom. You're going to have a lot of fast air traveling over the top. A lot of fast air traveling over the top for the frisbee, for the airplane wing, for a bird's wing. Same thing. If you have a lot of fast air going over the top, Bernoullis Principle states that the faster the fluid, remember air's a fluid, the faster the fluid goes over the top, the less the pressure is being pushed down. So imagine if you have fast air traveling over the top, which decreases the pressure being pushed down, then what does that mean about the pressure being up? The force being applied up is greater. Therefore, you get this thing called lift. Let's say it one more time. The greater the airspeed traveling over a bird's wing or an airplane wing or a frisbee, the greater that airspeed is, the less the pressure is being pushed down. Therefore, the greater the force and pressure is being pushed up, which causes lift. Now, how does this work with a chimney? There's 2 things happening here. For one, hot air rises. That's perfect. You have a fire, you're putting off hot air, that goes up. But secondly, Bernoullis Principle comes into play because you have a breeze and wind traveling over the top of that chimney. When you have that occurring, faster air traveling over the top, plus hot air rises, you have a greater up force in that chimney, which releases pressure even faster. So you're not going to have a buildup of smoke in your house because the combo of hot air rising and Bernoullis Principle, traveling fast breeze wind over the top of that chimney, you're going to release that smoke pressure very quickly. Okay? Same thing applies with the atomizer. What they're doing here is when you squeeze that little bubble, you are forcing air over the top of that tube. Now, inside that perfume bottle, you got a small tube going down, pushing air. Fast air travels over the top. What happens? Fast air over the top, less pressure down. That means the pressure to go up wins. That perfume travels up, and when you push again, you are now going to push the perfume out into the air. And those gas particles will fill the space provided. Okay, you guys learned that when solid, liquid, and gas was talked about. Whew, take a breath, guys. Pause this video. You did it. Good job. Take those notes. Go back. Rewatch it. Take more notes. Take more notes. Oh, I miss you guys. Care about you guys. I hope these videos are helpful. Send me emails. Send me messages if you guys have questions. I really hope you guys have an amazing Easter break. See you in the next video.